This video is about organometallic reagents in the use of epoxide openings. And this is going to end up being your number one carbon-carbon bond forming reaction in this course in Organic 1 because epoxides are fairly reactive. And so I've already shown you this overall scheme once in the epoxide video. And specifically, a base opening of an epoxide is just done by having some nucleophile go ahead and attack the less hindered side of the epoxide in an SN2-like fashion. And so the nucleophile is not necessarily minus charged in general, but for the purposes of the organometallic reagents, it's always going to be minus charged, frequently with the minus charge residing on a carbon. So this nucleophile is often a carbon with a minus on it, which is hugely reactive. And it's so reactive that it can do some pretty serious chemistry, although it might do E2 type chemistry with other kinds of leaving groups. With an epoxide, this is just spring-loaded and ready to pop open to relieve the strain. So you're more likely to do the SN2 opening than you are to do, say, an elimination type chemistry, although elimination is not out of the question. But in any event, nucleophile, come, do an SN2 reaction, pop open that epoxide, which then puts your nucleophile up with the oxygen down, because again, you had to come from the top of this in order to get the SN2 type chemistry to work. This then will sit at this stage with an O- for some time until you throw in a source of H+, and this is an acidic quench. So ordinarily it'd be like HCl in water or sulfuric acid in water or whatever. The identity of the acid doesn't matter. The fact that you throw in a little bit of acid and water is what matters, and you end up protonating the O- to make the alcohol. And again, depending on the exact details of what your counterion are, then you might show this reaction a little bit differently. Though, since you almost always have an acidic quench in water, the proper mechanism is always going to be that. You abstract the proton from H3O+, and you have a source of H3O+, because you have added acidic water. The main reason why I threw in H+ is because often that's the way you'll see it written on standardized exams, like say the MCAT or anything like that. What they'll frequently have is H+, which means H3O+, which just means acidic quench. This is the key underlying feature. If you understand this, then everything else I'm going to add is basically details and teaching you how to make the organometallic reagent so that you might use it. Again, you're going to be using this a lot in synthesis, and so though this is the best way of attaching a new carbon-carbon bond, you frequently need to make the reagent that's actually going to be doing the business end. So all I've done here is redraw this substrate again, and that's because I'm going to end up drawing some mechanistic stuff. So lithium aluminum hydride is a reagent that is essentially equivalent to sodium borohydride, except much more intense. It's a much stronger reagent, but it does the exact same thing. And so you've already encountered this in at least two contexts, but it can open epoxides. It's basically a source of H-. And so if you had, say, lithium aluminum hydride over the arrow and maybe THF below the arrow, the result would be, after an acidic quench, so we'll skip that step, just simply this, because you would have a hydrogen at this position, and of course we wouldn't bother to draw that. Sodium borohydride, likewise, would do the identical thing. What's convenient about lithium aluminum hydride and sodium borohydride is that they're commercially available. I just have jars of this stuff lying around, and sodium borohydride is not so horribly reactive that I can't just sort of, take it out in this little baggie to keep it from reacting with moisture in the air. It's fine. This stuff is reasonably safe, and you can use it, and you can buy it. They will ship it to you on a truck, and you can throw it into your reactions. Same thing, lithium aluminum hydride, I wouldn't casually wave around a bottle of it. It's vastly more reactive, but again, you can buy this stuff, and they will send it to you. It's a grayish powder, and you can throw it into your reactions. Very slightly more exotic would be sodium deuteroborohydride, in other words, with deuteriums instead of hydrogens. An extra neutron in each of those, and the only reason why I'm doing it is to show you how it would react in the end for stereochemistry purposes. But again, you would just see sodium deuteroborohydride over the arrow, again maybe THF down below. Again, there would be some implied or explicit quench of your material when all is said and done, so you would throw in H+ and some water, and the final product that you'd make would look like that. So the deuterium comes from the opposite side of the epoxide. If we had a chiral starting material, this would be achiral because you have a plane of symmetry now. If you had this chiral starting material, you now make this single enantiomer because again you have inverted at this position. The mechanism for this process naturally is identical. There's really no change. You open the epoxide as you'd expect and you get that. The next two are notable because they are not commercially available frequently, although you can buy some Grignard reagents and some organolithiums. In general, those you tend to prepare fresh. both because they're pretty reactive, and also because if you're making something complex, then again, you can't necessarily buy this stuff. So again, after workup, what you'd end up making is the R group up and the OH down, again, opening this single enantiomer to provide this single enantiomer. And then the last one, again, no change here, except that you can use an alkyne to open the epoxide. And once again, the alkyne must have come explicitly from the top, and you end up making this material when all is said and done. Now, it is generally my advice that you number the carbons involved when you are drawing these out, because this ends up being fairly complicated to keep track of depending on the exact details. For the remainder of this video, what we're going to do is illustrate exactly how these reagents are made so that you can use them in synthesis, and then demonstrate exactly what the products would be running these specific reactions under these conditions. So, how to make the organometallic reagents, how to use the organometallic reagents, again, in synthesis. The key reagents that will allow you to make the organometallic reagents, those are drawn right now. So you could just simply use those, write them down, this is correct. The mechanistic information that I'm about to provide is illustrative of how it works without actually being technically correct. So basically, what I'm about to do is wrong. I know it's wrong, but it does communicate something valuable. Having said that, an organometallic reagent, the way you make it is you take a chloride, a bromide, or an iodide, you throw in fresh magnesium, and either ether or THF, some ether type solvent, and that will produce your Grignard reagent. And so, if you do nothing but remember this is the correct information that I want you to store away. You make an MgBr like that. So what ends up happening is the magnesium basically inserts between the carbon and the bromine. You get a carbon-magnesium bond. That carbon-magnesium bond then gets used in synthesis. Likewise, lithium. You need 2 lithium atoms because you get 1 electron from each, and in the end, what you end up doing is making this lithium reagent, which then again you can use in synthesis. Actually, n-butyl lithium is one of the lithium reagents you can buy. So this you can buy commercially. It's horribly flammable. You can make your own from bromine and throwing in chunks of lithium. Any terminal alkyne with a hydrogen available, you can just simply react in an acid-base fashion in DMF, and that will produce the desired anion, which can then go ahead and participate in synthesis. And actually, I'm going to start my description mechanistically with this one, because this is actually the mechanism for it. You are simply doing an acid-base reaction. The bond between the carbon and the hydrogen is becoming a lone pair on that carbon, which you draw out this way. And the sodium is there visibly as a spectator ion. The minus is the thing that actually does the chemistry. So again, this is correct. The mechanism would be that the carbon minus comes by and does an SN2 to open that, and after an acidic workup, a quench, you end up making the product whereby the triple bond has added, and it has added up at this position, and since there was a methyl attached to the far end of the triple bond, that there is your product. By distinct contrast to this acid-base reaction, whose mechanism we understand very closely, what I'm about to draw is nonsense, because we know that this isn't how the mechanism works. However, it does provide the right sort of idea, because even though we draw this as a covalent bond with the magnesium attached, it also could be imagined to be some form of minus charged isopropyl with a magnesium plus floating around nearby. And we know that the reality of the molecule isn't this simple. We also know that the reality of the molecule probably isn't that simple either, but instead exists in some sort of weird complex thing. Likewise, the magnesium ends up inserting, but it probably doesn't happen by 2 electrons at the same time. It's almost certainly some kind of radical mechanism. 1 electron followed later by a separate electron and so on. So anyway, what I've drawn here is clearly nonsense. However, you can think of it as acting as though you have a carbon with a minus on it, and therefore this is an extremely strong base. The pKa for that particular system as drawn would be about 50 or so. So it's a very, very strong base and will react with water instantaneously to create fire and all sorts of bad things. So anyway, super reactive stuff that you are making. You're making a carbon with a minus on it, and you're doing so largely by exploiting 1 electron at a time so that magnesium can get down to magnesium 2+, and you'll have a bromine bound to it. Whether you think of this as being covalently bound, whether you think of it as having a minus on it, it acts as though it has a minus on the carbon. So the mechanism that I draw here is, again, probably not as straightforward as what I'm drawing, but you can think of it as the carbon-magnesium bond doing the attack to open the epoxide via a standard SN2. The product, as this mechanism would imply, would have a methyl up, an OH down after the quench, and now an isopropyl bound at this position and up. Again, having to come from from the backside of the epoxide. So that's what the Grignard will do. With the lithium, this is definitely going to be a one electron at a time process, and that's got to be obvious because we have one lithium with one electron, and then later a second lithium with a second electron comes by. But big picture, what you're ending up doing is pushing those electrons again onto the bromine. You need two equivalents of lithium. You are generating lithium and lithium bromide, and another Br minus is floating around. And again, it doesn't really matter how you like to picture it, whether you think of it as the lithium being covalently bound, as I've implied there, or whether you prefer to think of the lithium as being floating around nearby and there being a minus on that carbon. Again, functionally equivalent. Again, functionally pKa of about 50. Again, mechanistically, it's not entirely clear that this is a two electron process, but it could very well be, and then you're going to end up making the product that I'm about to draw. In this case, I used a different color to illustrate the butane that has been bound so that you can see that there are in fact 4 carbons bound at this position, and I would in fact encourage you to number the carbons involved whenever you do this, because otherwise it's really easy to lose track of how many carbons have been bound. It is incredibly easy in general to lose or gain a carbon when you are working on mechanistic problems. It is particularly easy to lose or gain a carbon when you are doing organometallic reagents. So again, recognizing that this part of the structure is unchanged and in yellow, and I've attached the new thing in a different color, and I've numbered the carbons. Those are strategies that I would use if I were you. Core idea is organometallic epoxide opening happens via an SN2 process, which then leads to a O-, which can then be quenched via acid. Since it's an SN2, the stereochemistry is inverted at the epoxide opening location. This happens largely because the epoxide is highly strained, which makes it possible for O- to be a leaving group, even though in general O- is not a leaving group. Synthetically, this is incredibly useful because we have a number of tools that allow us to put minus charges on carbon, and if a carbon has a minus charge on it, then it is ready for nucleophilic attack on an epoxide. So what you do is you take some carbon-bromine bond or carbon-chlorine or carbon iodide, and then you throw in a pile of magnesium and ether or lithium and THF, or if you have an alkyne, you can just do an acid-base deprotonation, as long as the pKa of the base you are using is stronger than a pKa of about 25 for a terminal alkyne. In any event, if you are trying to make carbon-carbon bonds in synthesis, my advice would be use one of the 3 tools I've illustrated here: a Grignard, an organolithium, or an alkyne to try to make your carbon-carbon bond. And again, a strong candidate for the thing being attacked is going to be an epoxide, or specifically oxirane, which is to say this epoxide specifically is useful for building up longer chains. Use these tools to build longer molecules. That would be my advice.